All right, let's check this out. Tomorrow we have this exam, and um, we have to cover fluids, waves, and thermodynamics. So let's go ahead and start by taking a look at chemistry. We'll start with Chem 1-1, and well, there's a lot of stuff we can look at, but I think what's important is we want to start with the fluid stuff first. Let's see where that might be. There's just so much stuff that this is more this is more thermodynamic stuff here, engines. We might as well start here. So we discussed Otto cycles in this class, and we found out that there was a whole bunch of different types of processes. So we have isothermal, adiabatic, isobaric, isochoric, and polytropic, uh, isentropic, I guess. Isentropic. I think there's all three of these words going to relate to that, but we have these different processes of different types of changes. We keep the temperature constant here, so we have no change. The Q is constant here, P is constant here, and V is constant here. So it leads us to these different conclusions. Internal energy zero, and we can go back to this formula here to figure out what the internal energy is, usually Q minus W. So that's sort of how we can sort of figure out these relationships based off all these, and keeping these constant. Um, so after that, why don't we take a look at the efficiency of these engines? Because these cycles, depending on which one you go through, you're going to go with a type of Q in or a Q out, which is like the total Q of the entire, if you go through the entire thing, you're going to get some kind of a Q in, which is going to be the sum of the positive Q's if you go through the system. So you're going to have like a positive Q here, a negative Q here, a positive Q there, negative Q here. You're going to want to add up the positive Q's, and those are your Q in, and add up your negative Q's, those are the Q out. And usually to calculate Q in a situation, we would want to use CV or CP and the change of temperature, and using this type of relationship to get the T. Remembering the box area is the actual work. And like I said, for these different types of processes, we hold certain things constant. So adiabatic, this particular change here, Q equals zero. Now there are these things about these reversible and irreversible processes. I think that this is correct. So I'm just going to double check on that though. So reversible versus irreversible processes. And well, I can kind of chart. I think. Leaving any change to the surroundings. Can proceed forwards and backwards. Proceeds only in one direction. One, two, okay. And the reversible happens super, super slowly. This one happens instantly. So this is correct. No friction. Yeah, no dissipation of energy, although there would be inside change of energy in total. We're talking about the universal total change. It's going to be zero, so that means the system and the surroundings in the reversible process are going to have the same entropy change. And irreversible processes, have a positive entropy change. And I think that means, well, I think when we have S being equal to 0, it's isolated. I'm not too sure when that would be the case, but yeah, let's go on to the next thing anyway. This is the relationship we can use if we're dealing with an adiabatic process. Uh, the entropy, there's all this there, yeah, so there's a lot of different ways to calculate entropy. We have this type here. We have this type here, which is for gases. And depending on whether you're using, scroll in a little bit here, depending on whether you're changing the P's or changing the V's, then, well, your V is going to be constant, so you can change the P's. This is equal to that, as long as you swap this out for the appropriate fraction here in terms of R. What I mean is that over here, we have the Cp minus Cv equals Nr, and we have these values for the Cp and the Cv. Let's not worry too much about that stuff there. It might be helpful to remember all these laws of gases, but I think the most important stuff is going to be, okay, so we did all of this, the kinetic energy stuff and the VRMS stuff. Because this is probably just something to memorize real quick. I mean, the VRMS is just 3RT over the molar mass in kilograms or just the mass in kilograms. If if you know mass or molar mass, depending on what you want to know. So usually it depends on what's given. Why would we use just mass or molar mass while solving for VRMS? This is for one particle, mass of one particle. Um, I guess I'll just put n single here. Okay? Because it depends whether you're trying to solve for the molar or just a single particle, a single atom. That's why we have all these different particular ones. So for you, you'd swap it out for KB, or you could use NR. Yeah. Over here you have R, or you swap it for KB. This is for the kinetic energy average. And this, this is just kind of like hard to remember all this stuff, I guess. It's all very similar. But if we think of this as like a tree root, like Doug Trio, like that little Diglett guy with the three of them, okay, and then he's basically this is the weight, right? So there's like a sack underneath that's weighing down, yeah. So you could think of that as like Doug Trio being weighed down with a sack, and that'll give you the RMS. Okay, and over here, this is just a single tree root here, so it's just one Diglett for the kinetic energy. And it depends if you want to use the KT, so uh, the cat version or the root version. And here as well, the cat or the root version with an N. You could think of maybe putting a Cheshire cat face on the Dug Trio, or the Diglett, just the Diglett. I know this is kind of weird, but this is how I can remember these types of formulas. Alright, anyway, so, yeah, and then over here, how are we gonna remember these? Well, isothermal, this reminded me of just flames, right? So these are flame. Adiabatic, I kind of think of just like the Italian word for hate. So audio is just kind of like a devil. So you could think of the flaming flames here, and then the devil pops out. Isobaric, that's P. So bears. I think you could zoom into the face, and he's baring his teeth, right? I believe. Uh, isobaric P pressure. Over here we have isochoric. So the singing choir. That's right. Yeah. So all of a sudden they're singing. And that will just help to remember whether it's temperature, because it's heat, whether it's the Q, which is the heat kind of. Temperature is temperature, heat is heat. Over here we have the P, the change of pressure. So maybe a push. There's got to be some kind of a squeeze or a push when we make translate that into an image. And over here the choir, the volume, so the size of the choir is basically what I'm thinking of. So these things are held constant. The efficiency here, we're going to be calculating either Q in or the Q out, as we discussed earlier, or we can use the work divided by Q in, and then we have this formula here, 1 minus T cold over T hot, and T cold up, really cold, really hot, T hot. Dang it. Sometimes I don't remember what I'm trying to say here. If we put this at absolute zero, then we technically get 1 efficiency, but that's impossible. Really cold increases the efficiency. Really hot increases the efficiency. And goes up if it's really, this is what I'm trying to say here, is that the efficiency increases with either one of those situations happening. All right? And the auto efficiency, we have to deal with the adiabatic processes if we're doing that. So we keep that constant. This is how we can deal with this issue. We take TF over TI, if we know that. It's the same thing as saying this. So you can just calculate TF over TI, and that gives you the denominator. Or if you have the volumes, you can, that's this, actually the same thing as R, and then you can use this thing on top. So how are we going to remember this TF over TI? I don't know, this is kind of more difficult. The change of temperature, the change of volume, and we have this R here. How can we relate TVs and Rs? Okay, if we have a television rotating around, so we just see this television rotating, so we got either the TV or the R version. Maybe that might help if we're doing an auto efficiency, keeping in mind that it has this exponent if we're using the R version or the V version. But that gamma minus 1 thing, while it's rotating, just um put it on a light pole or something, because usually gamma is about lights, so yeah. Alright, good enough. We have a TV rotating around the light pole, something like that. I think we pretty much covered most of the stuff on this page here. Zoom out a little bit. Yeah, we were kind of discussing the different ways to calculate the entropy. We didn't really finish that. Because depending on whether we have a gas, we use this type of calculation. Or if we're calculating the system, we would use this, which usually leads us here and there. Okay, so, but sometimes we have to do an actual integral, or sometimes we're using MC or NC. And sometimes the temperature is constant, like if we're in contact with the reservoir. So therefore, all we have to do is just use Q over the temperature. And if it's positive, then we're absorbing. If it's negative, then we are losing entropy. I think this is the heat loss. Entropy absorbed, entropy loss. All right, I think that's, yeah. Heat loss, entropy loss. Heat absorption, entropy absorption. If you want to calculate entropy across state changes and temperature changes all at the same time, it's just going to be a sum of all of the entropy changes. And usually, if we do this for example, with water, we might go from a negative temperature to zero in particular. Take that zero to fuse things, go from 0 to 100 with the liquid, take 100 vaporizing it, and then 100 to whatever temperature as a gas. And if we're calculating the temperature of this S of the universe, we can combine the system and the surroundings. The system is usually, we know the components of the system, so we could usually solve for that. Technically, most of the time stuff is zero, so often this is what we're really solving for. So I think this kind of concludes all this stuff. Oh, well, we didn't really talk about this absorption. No, there's so many things to discuss here, but yeah, how are we going to remember all these things? Well, I mean, it's more of the same type of thing. So we kind of start getting used to this. Start thinking isothermal means the temperature is constant. So, you know, you would end up with T, delta T equals zero. So delta U equals zero, giving you Q equals W. And then you can try to get this. So these are for the Carnot engine. If you're doing a heating process, you could also do refrigeration if you're doing it in reverse. So that's why we have basically these two things are essentially opposites of each other. Q cold, Q hot gives you, so okay, Q refrigeration for the Q cold is Q in, so it's Q cold, Q hot, Q out. I'm not 100% sure what these terms are referring to, but the idea is that you're going to want to get the out heat with, if you're doing a heat pump here, to calculate heat going out, the cold, but the Q in, if you want to calculate the refrigeration absorbed. So absorbed Q, Q in, emitted Q, Q out. Anyway, cooling, we have some different evaporation, compressing, condensing, and expanding. This is this process here. Okay, some cool little diagrams here. If we are dealing with monatomic, diatomic, or solids, we want to think about those things. And sometimes we might want to calculate the momentum, RMS, or momentum average. So M times V, RMS, or M times V average. Might be helpful to know how to calculate V average, which is 8 RT. So now we're talking about 8 piglets. I don't know, like 3 Doug trios. Just a massive amount of diglets. And they are getting, there's a circular, because it's pie. Maybe there's like a pizza or something. and they're weighing down by that sack. So it's kind of the same thing as the VRMS, but it's just slightly different with the term of 3 versus 8 and having a pi on the bottom here or not. And I think that I think you could also do the singular one just like that. You can do that here, there. I think so. Um, okay, so that was chemistry 1.1. Let's take a look at chemistry 1.2. And so we have to deal with like equilibrium stuff. Equilibrium is when we have maximum entropy. So the change in heat is no longer happening. There's no more heat going in or out. So there's no more entropy changing. And quasi-static means very slow. That actually means quasi-static means very slow. Well, that's cool. But I don't think that has anything to do with any of these three things. So I might have to actually delete this thing. Yeah, I think this is like a random definition I threw in there because I didn't know where else to put it. But if we're looking at steady state, then we're matching Q rates. We have to really check the cancellations here because when you match the Q rates, things will cancel on either side. So that'll make the equation simpler. If you're looking at a composite system, then it's actually really quite a nice equation here. You just figure out the Q rate is equal to A, it's the area of these system, a composite system, meaning you might have like 3 layers of different materials. And then you're going to sum it up with the R's. That's the resistance of the 3 materials, which is the distance. I believe this is the thickness of the material divided by the K of the material. And, well, these are the different capacities, depending on whether you just want quote unquote heat capacity or specific heat if you're using it with the mass or the molar version if you're using it with the moles. And constant pressure, constant volume. Yeah, Q of the system equals the sum of the Q's, which equals 0 because Q1 equals Q2 if you have a system that's in steady state or equilibrium as well. And so if you're changing states, you want to use this, but you can also get the Q rate by finding the mass rate. Okay, the change of mass rate. So you can get the Q rate if you know the rate of change of the mass. And over here, we have the different types of Q rates depending on whether we want to use the cat here. So I think on this one, I actually was seeing a cat, like a real cat. And he's also riding a skateboard here because this is the distance, so he's just riding a distance skateboard. All right, and this is kind of how we can visualize this thing. This is the hat. So, well, it's just a hat for the fluid, so you can think of just a hat with some water in it. That's great. And this, we probably don't have to deal with that one, so let's not worry too much. Over here we have the different types of things. So enthalpy is H, and heat Q. I think this is the molar enthalpy though. This is the molar enthalpy. So I'll just add that as a quick side note. This is the molar. You know how there's all sorts of different types. This is specifically the molar version. I'm sure that if you multiply H times mass, you'd get the mass enthalpy. Haven't had to deal with that yet, so I'm not gonna go too crazy about it. But move that right there. Call it the molar enthalpy. Okay. Um, so if we want to go through these different stages, we kind of already discussed that. But we'd have to calculate Q. You can either calculate the S going through the stages, or you can calculate Q going through the stages. And we have to be careful about all the leftover energy that we're given, because the leftover energy tells us information about whether the process completes or whether we don't complete it, whether we've gone over. And so we need to keep track of the leftover energies, and that's why we need to calculate these things step by step and literally get the numerical value every step and finish there, and then compare that with the next numerical value. This is one of those times that you want to be doing the numerical versions as you're going through Q Q stages, because you don't know. I mean, you can get like a full equation that might get you all through everything, but it might be a little bit harder to do that. But anyway, let's see what else we have here. These heat expansion things. It's not too crazy. It's literally just the delta heat, the delta length is going to be alpha times the original length times the delta t, which is just kind of obvious. So let's not worry too much about this one, but just realize that it'd be either 1, 2, or 3 when you're using the lengths, areas, or volumes here. And of course, that's the change in L, or change in area, or V. But if you want to find the new L, then you have to subtract the change from the original. So that'll give you the new L. Uh, Steady state. Alright. There's a lot of other stuff here, but I think that the most important thing was covered there. And then we have like this thing we might want to take a quick look at down here at the bottom. The triple point is here for water, and it's a very specific temperature, 0 degrees Celsius, and basically 0 ATM, well, 600, 6166611 PA, 0.00604 ATM. I mean, how are we going to remember that specific number if we're asked for a triple point of water? Christ almighty, but I mean, we might. I don't know. So, calculate some stuff there for more. I think we're pretty good on this. Let's go to the next page. I think at the beginning of this class, we were doing a bunch of complex analysis. So we might want to review that a little bit. Mainly this stuff over here that we have. Um, oh my god, this is so complicated. There's a bunch of coefficients that remain, these particular ones here. These ones go away because they're imaginary. Just there's like a very complex calculation for a lot of these. But I don't think that the complex stuff is too crazy. Maybe this. E to the IWT. That's pretty normal stuff. So let's just look at the diffy Q over here that we have recovered. About springs. Oh my god. First you want to check the spring, this thing. You want to check the squiggly thing. The squiggly thing is that's the damping ratio. Is the squiggly thing. Squiggly thing is the damping ratio, and you can think of it as B over the W. So B over W, what was that again? I was remembering this as specific images. B over W was beta. 2 beta Q. This is not this is not heat, is it? This is a different type of Q. This is just the unit, this quality factor Q. It's a random type of Q that we have here. This quality factor Q is related to 1 over 2 of the squiggly. The squiggly is B over the W naught. And once we calculate the squiggly thing, that tells us which thing to go to. We're going to be overdamped, we're going to be critically damped, or we're going to be underdamped. So it just tells us which one to use. Just beta over W naught. What did I remember that as? Can't remember. Um, Watts, power watts. Oh my god, there's so much stuff to think about here, though. There's like literally 1,000 things. What are we supposed to start with? Man, it took me like so long to go through all this stuff. The decay rate, B over M. Betas, 2B over 2M. And really, we're trying to solve these differential equations here using this guess of our solution. A star. And it leads us to this, x cosine of W naught. So this is kind of the one that we want to remember, because this is the amplitude, which is the square root of a squared plus b squared, which comes from these things over here. Tangent of theta is b over a. So that clears it up for that one. So you can find a and b if you know initial conditions. Once we go to the overdamped situation by adding a damping coefficient in here, now the equation becomes a little bit more complicated, and we have to try to plug in the prototype solution here, C E alpha A. This gives us this quadratic equation we're supposed to solve for alpha, and this one's a good one to remember because it's just alpha, positive or negative, is equal to beta, or negative beta plus or minus the square root of beta minus W naught squared. And beta minus, oh, I think these are bottles. Bottles, and I think that the W, I'm not too sure what the W is, but I think that the B are bottles. I think of B's as bottles. Maybe A's is apples. So you can see an apple, you got a bottle, maybe there's a negative bottle, and then you have to put the positive in the square root here. B squared. Ugh, a lot of stuff to remember. That essentially is the damped frequency, kind of. It's related to the damped frequency. If we want to know the damn frequency, it's very important to calculate damn frequency. We're going to take W naught squared minus the beta squared. And the half-life is ln2 over beta. And if we are doing the overdamped situation, like we were talking about, we are going to have the two real alphas. So we have two apples, depending on whether we use the positive or minus here. So these are going to be the solutions. A plus, and then there's a minus. If we go to the critical situation, then we have two equal alphas, because this term goes away, I believe. Well, no, the beta term goes away, right? What goes away? Something goes away. I think all this goes away. And then we're just left with this negative right here, which is actually the same as W naught, which makes sense. That's why we're in critical condition. Perfect harmony. And over here we have this answer, which is just A and then B. Here you're going to need to put the T there. The reason we put the T there is because we can't have two of the same solutions because you have the same solution, so it's just two different solutions here. If we have the underdamped situation, then we have two complex A's because this is negative, because this is less than this. And so we're underdamped. So now we have some I with this W prime being alpha. And remember that the W prime was calculated by using W naught squared minus beta squared instead of the other way around here. We are going to end up with these answers here because we can factor out this E beta T, and then we get all this stuff here. This actually is the same thing as saying this. And then we can solve for those particular things, maybe? There's a way to simplify this, and then we get towards this. This is something we also have to memorize. The C, E to the negative beta T, and we have the cosine of the W prime T plus this. But usually it's just the amplitude we care about. So let's just focus on C, E to the negative beta T. And if you can just get that, then that's pretty much one of the most important things about damping. So the amplitude of the underdamped is C, E to negative beta T. And calculate C by figuring out what A is. A e to the I theta equals C over 2. That's equal to A. I don't know what the heck. We've defined if we use tangent of theta here, then C2 over C1 comes from here. Usually we're given one of these things. So, yeah. Amplitude at time t. These things will cancel out. So you're left with the fraction of the amplitude at that particular time. It's usually when they try to say like, uh, reduced by, like the amplitude is just reduced by a third or something, then really it means that you're looking for a third of the amplitude. Or, yeah, exactly. Or a third of the C naught. Anyway, so that is pretty good for this stuff. It just gets a little too crazy and complicated. But let's consider now If we have springs together like this, it's the same thing as summing them up in parallel. Or if the springs are attached like that, then it's in series. Um, so if we go over to the decrement, the decrement D, so we might need the amplitude ratio after n cycles. So you'd want to get the decrement D. Now the decrement is 2 pi squiggly and 1 over squiggly. And the squiggly, let's just think of squiggly as a big C, like a big C, I guess, and squiggly C. I don't know, spring or something. So we could put 2 pi, we got this little spring, and then we have 1 minus the spring, and get the decrement there. And probably not going to have to deal with the full width half resonance thing. What we might have to do with this, the tangent of that phi right there in the particular solution is equal to lambda, or no, this y, this gamma, and the driving w divided by w naught squared minus the driving w squared. This is tangent of phi. Still don't know how I'm going to remember any of this stuff. This is way too much, you know? Max is proportional to the amplitude squared. And there's some ways to calculate that. So instant power. We have Ft times xpt. No, there's no way I'm going to be able to remember all this during an exam. Yeah, it'd be nice. We can obviously do it if we like review it, but there's no way to remember this, so we should just move on, I guess. I mean, we were solving these coupled oscillators in the beginning of class, and we can go over it, but how are we going to remember this stuff? This is actually not too bad if you just remember this little matrix right here. Tail ramp plus 0, a negative tail ramp, tail ramp plus 0. And trying to solve the determinant of this thing instead of equal to 0. Pretty wonky. It's a little too complicated to go into that stuff. So let's just move on. Heading into we need to take a quick peek at Bernoulli's stuff that we were looking at. The buoyant force in Bernoulli. Buoyant force is when you're floating only. So PVG, and that's the water weight displaced. I think you can use this only if you're floating. No way. Hmm. But I think the idea is that there's a difference. When you're floating, the object weight in newtons is more important because the weight is the water weight displaced, delta V. But if it's fully submerged, then the V is actually equal to mass over the density. Okay, so yeah, that's what's sort of the main difference is that you can calculate the the water weight based off, well, you can calculate the weight of the object, which is equal to water weight displaced, which you can calculate the volume of the water weight. Or no, the volume, I don't know. Jesus Christ, it's so freaking complicated. It's a good one here. So mg minus fb gives you the apparent weight. Because W is equal to work, so that's the apparent weight, where this is the W, the work, is pressure times the volume. You can integrate that. This is usually a change of volume. Otherwise, there's no work. So I'm just put a little delta right here. Mhm. All right. And then this density that equals the density of that. If the densities are equal, then the buoyant force is zero. Or no, the buoyant force is equal to the weight of the object. That means that they have equal densities. So the net force is zero. And then you can take F times D and you can get the change of kinetic energy. Okay. Fraction submerged is here. The volume displaced is mass over the fluid density. Oh, this only works when floating. Yeah, this only works when floating. There's so much stuff here. This is used for float. There. The volume displaced when floating is equal to mass over the fluid density. The volume displaced when submerged is equal to mass over the object density. Get that. Some different forces here. We got pressure. Pressure equals F over A. F required. Force required equals the change of pressure times the area. It was the force required to change the pressure. Okay, the force required to change the pressure. And Bernoulli energy over here. We have the H2GH V squared. And you have tension. It's kind of like the apparent weight And then we have constant flow, so we have for any depth, for any depth we have A1 V1 A1 V1 equals A2 V2. We can integrate that over the dA. Integral V dA. D. I think I should put NH. Any H might make more sense. I guess we'll just put depth. Because that's a dA, that's not a D times A, is it? I don't think so. Yeah. Alright. And P goes up simultaneously. The P changes simultaneously everywhere, giving us FA over FA. Now, if we're thinking about heights, then we use positive. If we're thinking about depths, then we use negative. This is joules per meters to the third. That's what pressure is. And I think we're pretty good on that. Anything else from down here? Not too much. I think this is pretty good. Let's close that. Electricity didn't matter, but we were looking at optics, weren't we? Because we have to kind of know a few of these things. Transverse pulses, transverse waves, traveling waves and standing waves. We have like velocities affected by the tension, we have the F sub n, F1, n over 2L, square root of T over mu. This is what we have to remember. Same thing as saying n over 2L Vx. To remember this, n over 2L, we could play no limit hold'em, Texas hold'em, two cards in your hand, and multiply that by the Vx, so just the velocity, so just fast poker player, I don't know, shuffling or something. Alright, and tension over mu, I think this one's pretty straightforward, square root of tension over mu. L equals n lambda over 2. This is the length of the entire string. And n is the number of loops that we have. First mode, n equals 1, 1 loop. This is the lowest. Something about shared nodes. And 0 is the first node there, and 1 is the first mode. System and oscillators. Energy equals something. We didn't have to do that. Beats are chill. Beats are super chill. We just beats is 5 BPS is equal to delta F of 5 frequency, 5 hertz. That's all we need to know about that. But here the path difference is not too bad. D sine theta equals m lambda. Mm, phase difference 2 pi d over or 2 pi um, delta over lambda. But delta is equal to m lambda. Okay. Delta y is equal to lambda L over D. There's no way I'm able to remember any of this stuff. It's just too much. Every time we bounce off of one of these things, we get a phase change of plus pi. We bounce off it twice, we're back to being in phase. Um, phase reversals. Here's the amplitude if you are summing two waves and they have a phase shift. 2a cosine phase over 2. And then here is just 2a if they are in the same direction, 2a sine kx if they're in opposite directions. dy over dx is a slope, not vy, just so you know. The vy is kinetic energy. The first derivative and the second derivative of that. Okay, well, I mean, it's gonna be hard to remember all this, but here we go. I think we're pretty good on this one. And honestly, we are basically done with the review. Might just review this last thing we're talking about over here in terms of like all these different Z's. But I don't think it's super important. Gosh. Mainly it's this idea that the total number of states, omega, is equal to the number of microstates to the power of the number of particles, or the number of iterations. And if you want to be doing like a subgroup of that and choose a specific number of some n that has a constraint to it, here's a good example. Let's say n equals 3 is the number of states that has 3 heads in it, if we're looking at a heads and tails situation here. Versus over here, if we were looking at an energy situation, like we have different energy levels, then in that situation, we might want to choose a certain number of particles found in one of these particular energy levels. So let's set the energy equal to n particles, or this is a small n from the total n, and that's multiplied by the energy of that level. Then you can actually use Stirling's approximation for all that, so it's kind of interesting. Leave you with this. the answer. And that allows you to solve for entropy if you want to. So it's kind of crazy. Um, the I discrete. Yes, these are all the microstates. You might have two microstates here, or maybe more. But the internal energy is equal to the sum of all of the energies in all the microstates divided by the number of microstates. And it'll give you an impossible answer because remember, these are discrete energy levels. So it's not like you can just have some fraction of this energy. You have to have that specific energy. But if you get this internal average here, energy, keep in mind that any of these energies, any of these values we calculated using the partition are averages because we're calculating in terms of microstates and probabilities, and so we're getting an average value. So this average value here is technically impossible, and it basically, oh, this is if we're getting to t to infinity here. This means that we have equal probability for all microstates, and so we could spend an equal amount of time in each one of those energy levels. That's the interpretation here. And then if we look at how to solve for u, there's a couple different ways. One of them is you could take the partial u of s, holding v constant. You get this relationship here, and then this is one way you could solve for u, because you'll get something on this side equals 1 over t, and then you could solve for u. You can also solve for v if you want. It's the volume. But you could also use this particular thing here, being a partial t of z, or you could use this one, which is a partial b of z, and they will all get you the same answer. Let's talk about these free energies, Gibbs free and Helmholtz free. And it's just basically whether we're getting the internal energy U minus the entropy loss, or we're using the enthalpy minus the entropy loss. And in this case, we use the partition function z. In this case, we use the Graham partition function, which is just it contains this chemical potential. We don't have to worry too much about that. Okay, so the partition function is going to be a sum of all the e to the negative b energies. You might be given an energy density. Integrate that over the energy. Phase space, this is exactly the same thing as doing this integral. This is what that integral means, and so that can be simplified to this interesting formula here, which can actually turn into a slightly more simplified formula because this equals that. Z to the power of n, if you're looking at n particles, right? It's because this is for one particle. You gotta let that sink in a little bit, because that is a kind of a mind-blowing thing. Okay, and then the probability of being in any one of those microstates is 1 over the number of microstates, or the total number of states, sorry, which is the max there. Multiplicity, dealt with that already. C equals 1 over z over here, by the way. When it says up to normalization, we don't have to calculate z. The probability's got to equal 1. That's the normalization idea. Usually we go from 0 to infinity to do that kind of stuff. microcanonical and the canonical states systems here. So if we have the energy constant, we're looking at an isolated system where the energy inside stays constant. We have an equal probability of all microstates. Hmm. And in the canonical, we hold the T constant because we're in contact with the reservoir, and we have a weighted probability. And now the Ti is this: equal probability, weighted probability. And just about concludes what we really need to talk about. We got a couple more things you can derive from the entropy, from the Z, and then you have F, and you might have E capacity, but these things are a little bit excessive because we have other simpler ways to calculate those. So, yeah, it's quite interesting, but all of this was quite difficult. Hopefully this helps out for the exam tomorrow, if anyone is watching any of this kind of stuff.